Yeah, are you doing it to the cloud, which is usually simpler?
Got it. Yep, that's going to the cloud, I think.
Okay, good.
Okay, so should I start?
No, we'll wait till 2:02. So we add
Okay,
it to 2, and then we give people a couple of minutes to show up. And then
sure.
you can go till either 5 of or 10 of, depending on how many questions you had during the talk, and we leave time at the end for questions. And we'll watch the chat also. So if people put questions on the chat, we may stop you with those.
Okay,
Yeah.
sounds good.
So have you had a lot of interest in this work? It seems quite interesting to me.
Yeah. Yeah, so there's been positive feedback. Yeah. It's very new.
Yeah,
So it's, I'm also very excited about it.
yeah. Yeah, I've done big numerical Feynman diagram calculations, and I had exactly this thought: shouldn't there be some way to sample approximately?
I see. Okay. Yeah, it's yeah, okay. I mean I'm aware that this is also a bit of a mixed audience, so I will yeah, I'm trying to kind of give a broad overview
Right,
of what's happening and why this is interesting and so on.
right,
But
right.
yeah, okay, if you already worked with this, then you will probably have to wait a bit for the interesting part
That's
for you.
fine. That's
But
fine. Yeah, I see. Your mouth is cut off. Your image is a little okay.
what is cut off?
No, you're fine. You're fine. It's she and our colleague who's kind
I
of
see.
looks like he's swimming.
Hi.
Uh, was our first real talk. We had many workshops at the beginning of the year, and so we'll see how many people show up. In any case, many people watch our recordings. So it's 2:02. Why don't we get started? Okay, so I'm Mike Douglas, and this is the New Technologies in Mathematics seminar of the Harvard CMSI. And as in previous years, we have a combination of topics, anything which covers new technology, which is usually almost always computing and sometimes AI in the service of mathematical and scientific research with many related topics, developments in AI, developments and other sorts of computational technology through improving numerical methods, that sort of thing. And so today we're very happy to have Michael Borinsky, who will tell us about new formulation of quantum field theory that allows efficiently sampling the perturbative calculations. So I think this may change the way we think about quantum field theory. Michael's at the Perimeter Institute. As always, we'll watch the chat. And if you have a question that you're not sure about, you'll put it in the chat and we'll either ask it or answer it if it's an easy one. And we'll have, of course, several minutes for questions at the end. And is the recording going, Blake? I don't see a.
Yes, it's going.
Okay, good. Oh, yeah, there I see it was just covered under thing. Okay, so without further ado, Michael, please.
Yeah, thank you very much for the kind invitation and the super kind introduction. So this is yeah, about tropicalized quantum field theory. So I hope you can all see my cursor. Uh, And the subtitle is Global Tropical Sampling. So it's about sampling eventually of the Feynman graphs or the perturbative contributions in quantum field theory. And this is the reference for the arXiv article. And I know that this is kind of a mixed audience I'm talking to today. So I will give like lots of motivation and background on these notions. So I'm trying to give also like an introduction like on what these words also mean and why this is very interesting in physics. So both the tropicalization and the quantum field theory. So please feel free to interrupt me to ask questions. Okay. So the motivation for this comes from quantum field theory, and it particularly from the perturbative approach to quantum field theory, where so this is a specific approach to quantum field theory, and it's also the only generally effective approach to quantum field theory for the quantum field theories we care about in nature. But if that does not mean anything to you, this quantum field theory, then a different angle of this is that ideas from a specific simple type of geometry, so-called tropical geometry, are here applied to specific very hard numerical problems or integration problems. And also algorithmic problems. So it's also about complexity theory of these kind of problems. So quantum field theory, brief introduction. It's the language of fundamental physics. So it's kind of the programming language in which we formulate the physics of elementary particles. And its predictions are also used in statistical, in condensed matter, and in particle physics. So particle physics most prominently, but it's actually broadly applicable. Today, it's even used for predictions in gravitational wave astronomy to a certain extent, at least. And one like stellar feature of quantum field theory is that it's one of physics' most accurate tools. So the crown jewel is like one prediction up to 1 in a trillion accuracy of the electron's magnetic dipole moment. So that's a very, very accurate prediction, and it's hard to match that. So here also with Harvard contribution, there's a recent measurement of this value, and it agrees with it also gives like then precise implications with like of nature's constants up to like many, many digits. I think these are these 9 digits here. Okay, so however, there's a paradoxical situation here. So on one hand, quantum field theory is a super accurate method to make predictions, but there's a key deficiency of quantum field theory. And the deficiency is that making predictions is computationally very expensive. And I'm going to try to give you an idea of this workflow that is necessary to make a prediction in quantum field theory. It's roughly the following one. So this is only a sketch here, of course. So we have some quantity P in H bar. H bar is some parameter. H bar is actually the traditional one that is assumed to be small. And then we expand the interesting quantity in the small parameter. And the coefficients of this expansions AL, they can then be computed explicitly by summing over graphs G here. And so these graphs, they have a specific shape, and we restrict the size of these graphs in a specific sense. So traditionally, we restrict the loop order of these graphs. So this is what I call here LG. And each graph is weighted with a specific object with an integral. And these are the famous Feynman integrals, these I of G objects down here. So just to quickly summarize, H bar is an expansion parameter. The sum contains all graphs. There's a specific shape to these graphs, and L dictates the number of loops of these graphs, and IG is a weight for each graph that is the Feynman integral. So there are two problems with this approach. The first problem is that the computation of these Feynman integrals is very hard. So these weights are very difficult to obtain. The second problem is that the number of terms in the sum for each coefficient, the number of graphs we need to compute, it grows factorial. And I wrote here factorial because this is not an explanation mark, so it really grows like L factorial, the size of the sum. So a bit more detailed, why are these integrals complicated, or how does it manifest? So at low loop orders where where physicists want to make phenomenological predictions, like for experiments at colliders like the LHC at CERN, we need these integrals computed at low loop order, and there's a lot of intellectual energy invested in the evaluation of these integrals and in writing them in some kind of analytic objects or known analytic functions. And the methods to do so, they are very highly developed and partially at the forefront of algebraic geometric tools. So there's a very fascinating interaction between algebraic geometry and the nature of these integrals and also number theory that has been very inspiring also for mathematics. To illustrate the complexity of these individual integrals, I want to mention that even answering the question, is one of these integrals for a given graph finite or not? So this is like a coarser question than what's the actual value. The question is just, is it infinite or not? Even answering this question takes, in general at least, exponential time in the number of edges of this graph. So it's a computationally hard problem to even answer this yes or no question if it's infinite or not. And the fastest known numerical algorithm for evaluating these integrals, it's actually via tropical sampling. So it's also already a tropical algorithm. It scales with the number of edges of the graph times 2 to the power of the number of edges. So here's this exponential growth rate. And this is the same exponential growth rate we need, the exponential time step we need to answer the questions if it's finite or not. And after this pre-processing, there's actually a polynomial-time evaluation algorithm that just scales with the delta to the power of -2. Delta is the relative accuracy. We want to evaluate these integrals. And this is then via Monte Carlo steps. So this delta to the power of -2 scaling is typical for Monte Carlo processes. And then we have only a polynomial time scaling in the number of vertices of the graph. So the problem number 2, why is that hard? So with that, even if we would know like all these Feynman integrals instantaneously, we still have L factorial many problems of this size to manage. So the runtime, even if these IGs would be available, these integrals, would still scale as L factorial. And the number of accurate digits we get out of such a prediction in this way also scales factorial with the number of digits. So the runtime to make the prediction also scales factorial with the digits that we want, because the number of accurate digits also scales linearly with this loop order L, roughly at least. So this is, of course, like for theoretical physics, this is a big problem, because now we know that measuring a quantity like this magnetic dipole moment of the electron, it only takes polynomial time or money and resources, because everything in the real world at least only takes polynomial time. It can be like a large polynomial time factor, but the size of the experiment that we need to measure these digits, it scales polynomial. And therefore, eventually predicting this number or making these predictions becomes harder than actually measuring these quantities. So naively, at least, measuring is eventually cheaper. The computers we need for the prediction eventually become more expensive than the apparatus we need for the measurement. So this is like the motivation. But now, why are these integrals so hard to evaluate? So what's the precise problem? So these are just ordinary integrals after all, or more or less ordinary integrals. Why can't we just plug them into Mathematica and ask Mathematica, please, and integrate it for us? What does that make? What's the source of all these complications? And we can, of course, try to do so, but it doesn't work because, so the most amenable representation of these integrals, it's an algebraic integral, actually. So this is mathematically like a very sound object, where we integrate over the positive orthant taken of the dimension to the number of edges of the graph. So we have an integral of the dimension of the number of edges. And then the integrand is the inverse of a specific polynomial, P of g, in these values in the orthant. And we take this polynomial to some power, for instance, to the dimension of spacetime. But this is an algebraic integral that we have to evaluate. So this Feynman integral corresponds to this algebraic integral. And the complication is that these integrals, they exhibit very complicated singularities. So they have algebraic L1, so integrable singularities, but still not L2 integrable singularities. So black box Monte Carlo algorithms to try to integrate these objects, they fail quite hopelessly. And for people who have maybe not spend so much time thinking about this, I like to give my favorite example of why this problem pops up. Here's a toy example, and in these Feynman integrals, this specific example is leveraged to like a much more complicated extent. So this is an integral over the unit square, and we integrate 1 over x plus y, so in 2 coordinates. And it's very easy to evaluate this integral over the square. It's just 2 log 2. But suppose you were very lazy today and didn't really want to do the work to evaluate this 2 log 2 number, or that you're working with a computer and it's cumbersome to program the computer to understand this transcendental number log 2. So you want an approximation, some alternative, and you want it to be easy. So the naive approach, the naive Monte Carlo approach, works as follows. We throw darts on the square. So we tell the computer, please give us many samples, x, y, that are in the square, so in this interval squared, 0 to 1. And we want these pairs to be distributed in the square uniformly and randomly, of course. And then what we hope is that if we then evaluate the integrand, so this is 1 over x plus y, many times with like capital N many darts we throw on the square, and we average over all these samples, that we get some decent approximation of our original integral. But of course, there's a caveat, and this does not work because we forgot to include the variance inside the consideration, and the error term. And the error term, it scales famously at the order of the square root of the variance over the number of samples that we take. So this is a famous consequence of the central limit theorem in statistics. And in this case, if we look into this variance that we can actually very easily estimate, so the variance is just the square of the original random variable minus something else. That doesn't really matter anymore because we immediately find that this integral that we started with is not square integrable, so it's just infinite if we square it. So the variance is infinite, and therefore we won't get any convergence with our naive Monte Carlo approach. So no matter how many starts we throw, we won't get like a good estimate of our original integral 2 log 2. And these kind of problems, they are amplified to a huge extent in these algebraic problems that quantum field theory poses to us. And the same type of problem, so this is now problem number 2, we can also think, yeah, well, there's an obvious idea to avoid the super exponential number of terms in these sums to evaluate these perturbative contributions. We can just sample graphs uniformly and randomly, but this also does not work, and I actually made sure that this really does not work with my student, Andrea Favorito, who did a fantastic job, where we just sampled like where we evaluated many integrals of this type, and then showed empirically at least that they also follow a heavy tail distribution. So this is a histogram of the logarithm of these integrals IG, and you can see that there's here this tail, and in like actual coordinates, this tail actually turns out to be heavy in the sense that it spoils this convergence with respect to the central limit theorem. So uniform sampling for these estimates of these kind of objects does not work. And yeah, these problems that quantum field theory poses us, they are just not, they're somehow, they don't really like to be treated with this naive approach. So we have to develop something more fancy. So here also naive sampling fails. So we need to do better than uniform sampling, and this is where this tropical idea comes from. And this is a special case of so-called important sampling. So we don't sample uniformly, but we sample via a non-democratic process. We favor specific points, specific graphs in our integrals, and such that we catch like more important contributions, for instance, inside these heavy tails with higher probability. So what's the basic strategy behind this? It's also very simple. So suppose we have such an algebraic integral again over the positive orthant. The integrand is now just a polynomial p of x for simplicity, and we just integrate over these coordinates x1 to xn. We can just trivially rewrite this integral for any function f sub p. So we just introduce some function f sub p that also depends on x, and we just wedge it into this integrand without changing anything. So we change nothing, but now we design our function f sub p in a specific sense to help us with our sampling problem. And so what we want from this f sub p function is, so we want to choose it such that first, this correction factor, or this kernel fp of x over p of x, remains bounded in our integration domain. So px is what is in the kernel of this integral now. And we want it to be bounded, and we want it to be bounded within a small corridor as possible. So we want it to be bounded from below and above, if possible. But from above is more important. Then we want fp itself to be positive, because eventually we want to interpret this part here of the this last part of the integral as a probability distribution. So we want that to be positive. And last but not least, the most important thing is, of course, that we want a good sampling algorithm for this measure here in the back of this thing. So we want to be able to define a non-uniform and non-democratic measure on our domain, this mu of f measure, and it's supposed to throw out points proportional to this 1 over fp x function. And yeah, so ideally we would of course have something that is as close as possible to our function p of x, but yeah, so we have to have something that is simpler to evaluate because, for instance, we have to compute this normalization factor up here in the front, this 1 over z factor, and the computation of this normalization factor has to be simpler than computing the integral itself. Otherwise, we wouldn't really have gained anything. So if we have something like this, then we can evaluate I, our original integral, by sampling points from our measure mu of f and evaluating this fluctuation term, this kernel, often via a Monte Carlo process. So this is the basic idea. And now what is a surprisingly good balance, or what works very well in practice, or is this tropical approximation. So there's some help from geometry, and this is a particularly combinatorial type of geometry called tropical geometry that helps in this case of these algebraic integrals. So here we just take such a polynomial p. It depends on some parameters, and it depends on some coefficients, and it's some suppose the coefficients are all positive, so it's a polynomial in R plus of these variables x1 to xn. And then we define this tropical approximation by replacing the sum with a maximum and throwing away all the coefficients. So yeah, we just so the rule is just the sum becomes a maximum and the coefficients become all 1. And this gives us a decent approximation of our original polynomial. And if you know tropical geometry, then you know that in the tropical ring, we typically not only replace the sum with the maximum, we also replace the multiplication with addition. And this can be recovered in this language by using logarithmic coordinates, which is very important under the hood, actually, of these kind of methods. But yeah, so this is very much related to the actual tropicalization in the tropical ring, just as a side remark. But if you have never heard about tropicalization and tropical geometry, this is the way to go. Okay, so there's also an alternative viewpoint of this as a deformation limit. I just want to mention this. So we can also interpret this as deforming our original polynomial p by giving a power eta to each of the variables we put into it, and then taking the eta square root of the resulting object, and eventually taking the limit of eta to infinity. So it's also kind of an L infinity limit of our original yeah. So it's it's a specific deformation limit of our original polynomial p, and we can in principle interpolate between p and p trop via this eta trick if we want. So the tropical sampling strategy now is to use this p trop as such a function fp as I described before. And this is a theorem from 5 years ago that this actually does the job decently well. So this ratio is bounded, this tropicalization is trivially positive, and we have a fairly efficient, so efficient is like, it's not really polynomial time, but there's a fairly efficient sampling algorithm for these measures mu f, where we now have this fp being equal to this p trop polynomial. There are some specific cases still. So if we know now something about these polynomials p that we start with, so this is where more of the tropical geometry comes in. So if these p of x are of special type, and the special type means that the Newton polytope of p of x is a generalized permutohedron, it's a very specific class of polytopes, then we have a relatively fast algorithm to sample. So we have a quite fast already. It's still exponential time, but it's much faster than anything that you can do without this property. And thankfully, the Feynman integrals in quantum field theory, they exhibit this property. And this leads to this runtime that I mentioned before, where we have this exponential time preprocessing step and then a polynomial time sampling step. And this exponential time preprocessing step, it comes from generally understanding this generalized permutohedron, this polytope. So we have to compute a facet presentation of this polytope, and it just happens to have exponentially many facets. So computing it takes exponential time. We cannot really do anything about it within this framework. And yeah, so this exponential runtime really also effectively just comes from computation of the prefactor. So this normalization prefactor, which we also need to compute, which is just the integral over the tropicalized version of the polynomial we started with. There's an algorithm to do this, and it works recursively, but the recursion just takes exponential time. Okay, so now back to these problems. There were the two problems, the problems with the individual Feynman integrals and the problem with the sum over all of them. We now had some partial progress towards the first problem. We have at least an exponential time algorithm to evaluate these individual Feynman integrals, but so far no progress towards problem 2. We still have factorially many Feynman integrals to evaluate. And this is where now this new work starts. So this is the work from last month, where some progress is achieved towards the second goal. So the strategy is to replicate what we did before for the individual Feynman integrals on the level of the full quantum field theory. And here again is the sketched workflow where we expand some quantity of interest in terms of some small parameter, and then each of these coefficients of the expansion can be written in terms of Feynman integrals. What we want now is we want to tropicalize this whole thing. And we do it, of course, from inside out. So we know kind of how to tropicalize the individual Feynman integrals. We learned that, we just write them down in this algebraic way, and we can replace each IG with its tropicalized version. And then we discover like a tropicalized expansion coefficient, and we can sum up these expansion coefficients and get some kind of tropicalized prediction of our original quantum field theory. And the first insight of this new work is that of the new paper is that we can really make sense of this on the level of the original quantum field theory and interpret this whole theory's tropicalization as a deformation limit of the original quantum field theory. So bear with me if you're not familiar with this quantum field theory language, but a quantum field theory can be written in terms of an action functional. So I wrote it down here, an example of this. So we have S, it depends on a field phi and a source field J. And then we integrate over a base manifold, and that's in this case, it's RD, and we already introduced like a parameter xi, which is going to be our deformation parameter. So we integrate over this RD times psi dimensional space. And then we have a kinematic term, which involves the square of this phi field. And in between, we have the D'Alembertian or the Laplace operator on the space manifold. We also have a mass term. But here we also introduce this deformation parameter already in hindsight. And then we have different like interaction terms and source terms for this quantum field theory. And then the eventual partition function of the quantum field theory is written as the path integral over this action functional, where we integrate over all field configurations phi. Unfortunately, mostly these path integrals don't really exist, so we can have to think more of it as a formal expression that just tells us how to expand these objects. But it's a good device to remember the structure of these things. So in this picture, the initial quantum field theory, it's achieved if we set this deformation parameter psi to 1. So there we have just an ordinary quantum field theory over a d-dimensional space. And this propagator term, this kinematic term, is just the usual quadratic Klein-Gordon term of a scalar quantum field theory. The first result of the recent paper is now that if we deform the quantum field theory and set this and approach the limit of psi going to 0, and actually we have to approach 0 from above, then we achieve precisely this tropicalization of the whole quantum field theory. So we can also interpret this tropicalization as some deformation limit of the full quantum field theory. But as a disclaimer, I have to mention, of course, that most of the dynamic behavior is lost with this tropicalization. And if you remember, like from before, this tropicalization also throws away all these coefficients of these polynomials. And the dynamic behavior, it also hides in the coefficients of these polynomials and these algebraic polynomials. So it cannot really stay at least not at a very large extent this behavior on this dynamical behavior of the quantum field theory. But then there's a key step or a very important observation, or the most important observation in this work is that this tropicalized quantum field theory is now exactly solvable in a specific sense. So, and the theorem is that this tropicalized deformation limit or all the data of this tropicalized quantum field theory can now be computed via or is fixed via a certain nonlinear partial differential equation. And here's a picture of this partial differential equation. It's actually, I mean, it looks a bit unweirdly, but it's actually a bit, it's actually not too complicated. So the object here or the unknown in this PDE is gamma trop. It's the so-called effective action of the tropicalized quantum field theory. And this PDE, it fixes this effective action completely up to trivial boundary conditions. So we have to make sure to have the right boundary conditions. If we have 0 coupling, for instance, so these are trivial boundary conditions. But besides this PDE fixes the behavior of the tropicalized quantum field theory completely. And PD is a differential operator that has a bit of an unwieldy shape, and this gamma trop is a function in the space-time dimension D in a parameter phi that enumerates the external legs of the quantum field theory and then all the coupling parameters. So this is actually pretty easy to extract like values for this gamma trop, at least numerically or perturbatively from this PDE. Okay. Some illustration of the proof of the solvability. So this proof, it exploits a recursive combinatorial relation between the tropicalized version of these Feynman integral. So the proof works perturbatively, and also the statement is so there's yeah, it's only like a perturbative statement, strictly speaking. So it tells us that if we hit a tropicalized Feynman integral with a specially crafted operator, PD, then we arrive at smaller tropicalized Feynman integrals where we have like one special edge, which is pink here. And we have this kind of necklace of graphs, different combinatorial possibilities that we can encounter if we apply this operator PD. And these different possibilities, they combine into a geometric series. And this geometric series is precisely why we have this 1 over 1 minus this second derivative of this gamma trop popping up. Yeah, so this is also, so I call this also the tropical loop equation because it increases the number of loops of these graphs by 1. So here on the left-hand side, we have 1 loop more kind of than on the right-hand side. We can compute the left-hand side by knowing everything on the right-hand side up to 1 loop order lower. Okay, so there's a computational consequence which is kind of immediate from this PDE. It is that we can translate this PDE into an efficient way to compute the coefficients of this tropicalized quantum field theory. And in fact, it turns out if you are a bit nifty with these computations, you can compute these coefficients now in polynomial time. The computation of these coefficients works via certain nonlinear recursion equations, but they require only polynomially many steps in the loop order and also the number of legs of the graphs that are also important, but I don't really talk about legs of graphs in this talk. So we can compute all the observables of the tropicalized quantum field theory very quickly. And this is a first hint that we can then design fast sampling algorithms for our original quantum field theory. Yeah, so you might already see where this is going. So here's an example. So we can just compute this gamma trop object up to many, many orders. So we can ask the computer, please give me many, many coefficients. So here I wrote them down as rational functions in this space-time dimension parameter and also in this coupling parameters. And you can just compute many coefficients via these recursions. And so this is very cheap. Now, so the same computation would be very expensive in actual quantum field theories.
Can I ask, you have a
Sure.
lot of singularities at physical values of D. Are we going to continue and then somehow bring D back to a physical value at the end, or what are we going to do?
Yeah, so this is just, so you can just think about this expansion as an expansion where each coefficient is a rational function in D. And each coefficient, as such a rational function, the coefficient can just have singularities in D. So it's just sort of computing the non-renormalized tropical effective action, the bare one. But if we fix D to 4, for instance, it's going to have many poles in D. So it's regular. So there's like this dimensional regularization, and the tropicalized quantum field theory is regularized in the dimension as well.
Okay, so we do look at a different D, and at the end of the day, we bring D back to 4 or whatever it's supposed to be.
Yeah, so I mean, in principle, it's still going to be infinite eventually if you look into phi to the 4th theory in 4 dimensions. So where there are tricks on how to get finite observables out of this. But in this paper, I only fully tackled super renormalizable quantum field theories, where we are in low enough dimensions such that we can actually
Oh, so
that
these echo the standard quantum field theory divergences you're saying.
Pardon?
These are like echoes of the standard quantum. You have the standard quantum field theory divergences, and you.
Yeah. So actually, the feature of one characterization of these tropicalized quantum field theory is that it has precisely the same divergences as the
Okay.
original
Oh,
quantum
good.
field theory.
Okay, good. Thanks.
So it's like the only fit. It exactly mimics like all divergences in all space-time dimensions.
Okay.
So there are quantum field theories like 5�3, for instance, in 3 dimensions that have no perturbative singularities.
Yeah. No,
And then,
you explained it now. Let's keep going.
okay.
I have a question. I'm a little lost about what this object tells you. You started about talking about scattering amplitudes, and now you have some effective action, which is a polynomial in the fields. I mean, does this let you compute the scattering amplitudes? Why are there no derivatives acting on the field? What's going on here?
Sorry, what are the fields?
What
Yeah.
is this thing?
So
What is it good for?
this is so this is only a function. But this is like this is how the effective action behaves in this tropical limit. So
This is
here's the picture.
putting
We took this.
Right.
We took this. So here we have the initial quantum field theory if we just set psi to 1. But if we send psi to 0, then we arrived at this tropicalization. And z psi is the partition function of the original quantum field theory, but there's a series of transformations. So you have to take a logarithm and then the Legendre transformation, and then you arrive at the effective action of the quantum field theory. But it carries the same information as the.
But what you're writing doesn't look like an effective action. There's no derivative. There's a
But
local
the answer, I think the answer is this is just a device we're going to use it to derive these weights for graphs, which capture like a leading singular behavior of the amplitudes, but they're not the amplitudes. So we'll then put them in the sampling procedure to make the sampling procedure work better.
Yeah. Yeah, so there's one step that I actually swept under the carpet here, but it's implicit in the statement down here. So these derivatives that you mean, they reflect the dynamic behavior of this quantum field theory. This dynamic behavior, it's trivial. So there's no more dependence on the external momenta in this tropical limit.
So is it like an effective potential then? Is that what you mean?
It's an effective action. So it's not really like a
Well,
potential.
it's like a potential because you're not putting in momentum fields that depend on space-time. But again, it's like a device. It's used to calculate these useful weights that will go into the sampling procedure. It's not in itself a physical thing.
Yeah, it has I mean, we can. Yeah, so physically, it's a strong word, but it really pops up in this deformation limit psi going to 0.
But just tell me, so this gamma tropical that you computed, what do you use it for? How does that tell you something useful about the?
Yeah, this is what Mike was saying. So this is a device now for doing the sampling.
So for doing numerical sampling,
Yes.
it's like a change of variables to make you more efficiently evaluate the integrals. Is that what you're trying to do? I mean, I guess I'm a little.
So
It's a change of measure, as he was describing.
Change of measure. Yeah.
So this is the idea. So the strategy is really that we want to find this important sampling object, this f or p of x, and this tropical cartoon of the original polynomials serves well as kind of a cartoon version with which we can sample. And I want to replicate this on the level of the full theory. So I want to replace each Feynman integral with a tropicalized avatar, which is simple, and does not have any kinematic dependence, but the value of the tropicalized avatar, it should correlate well with the original Feynman integral. Does it make that clearer?
Yeah, it makes more sense. Okay, well, maybe I'll wait till the conclusion slide to figure out what you did.
So this is the idea. And this is only, in this case, this is possible in polynomial time now, thanks to this exact solvability of this tropicalized quantum field theory. Yeah, so there's also a geometric interpretation that I really like. So we can think about this tropicalized expansion as some integral, or as, of course, the sum of all graphs. But so we have to weight each graph by one of its automorphism groups. So these are the symmetry factors that appear in physics. And then we have this Feynman integral, and I wrote this toy version of the Feynman integrals, but it's already like almost the full complexity, where we have some polynomial p, and in the tropical case, we just replace this polynomial with its tropicalized avatar. Now, one thing that we can do, and this is just an interpretation of the sum of all graphs and these integrals that have the dimension of the number of edges of the graph, is that we can just interpret the sum and this integral together as an integral of our modular space, of metric graphs. So this is a modular space of graphs, MGL. And these modular spaces, they collect all graphs with edge lengths assigned to them into one geometric object. And this form, this integrand, is then a volume form on this modular space. So here's a picture of this modular space of graphs. So each point in the modular space of graphs is a metric graph. So I illustrated here two red points, and they represent some graph with assigned edge lengths. So each edge has a specific length. The lengths are parameterized now by these parameters, x1 to xn. In physics, these are the Schwinger times associated to the specific propagator. And if we move around the modular space, we just change the lengths of these edges somehow. And in particular, we can go to the boundary of the simplex and shrink one of these edges to a point. And we also usually identify isometries in this modular space, and we can think about very interesting limits. And I really like I like these kind of modular spaces, and they have very, very interesting applications in group theory and mathematics in general.
Can I ask, is this a mathematically known definition of the measure on this moduli space? I know this.
No, this is a new yeah. So I mean, this is like just inspired from physics, of course,
Yeah.
but this is not a traditional measure that
Okay.
mathematicians have considered on this modular space. No.
Okay.
Yeah, I mean, it's obvious from the physics interpretation, so this is just an alternative interpretation. So I just want to mention this. Yeah, so as a remark here, of course, is that the nonlinear recursion equations that compute these perturbative expansion coefficients here of this gamma trop, they have an analogy in the world of a different modular space, the modular space of curves, where Maria Mirzakhani wrote down in her seminal work volume recursion formulas for volumes on the modular space of curves. But there, of course, that Mike said the volume form is the Weil-Petersen form, which is a very classical object, and here it's just a very auxiliary object inspired from physics. So this is only a geometric analogy, therefore. Okay, so if there are no more questions, so what we can do with this is we can now interpret our gamma trop coefficients as some integral over the modular space of this graph. So we just integrate over the space of all possible metric graphs. So these are pairs of a graph and some assignment of lengths on these edges. So just integrate over this kind of space, and mu trop is just this volume form which involves this p trop g. And now I can answer this question that Matthew had before. If Matthew is still around, I don't know. So what we want now, of course, is to interpret this measure again as a probability measure on the space of metric graphs. And this brings us back now to the original gamma L. So this is the effective action of the actual quantum field theory, the original one that is not deformed. There we can also write down the coefficients as this sum of our graphs. And we weight each graph with one of the automorphism group. But here we replace the polynomial again with the original PG, which is not tropical. And then we can just wedge in this P trop integral and replace our volume form with mu trop. And we now have some integral over the modular space of graphs with an undemocratic measure. And we have a correction term, P trop G over PG. But we know from our tropical insights from before that this correction term is bounded and it has all the nice properties that we want. So the only thing that is missing is now still a sampling algorithm for these metric graphs that are distributed like mu trop on the modular space of curves or modular space of graphs. So what we need is a global sampling algorithm for metric graphs that are distributed like this measure mu trop. And that also leads to a well-behaved Monte Carlo algorithm to evaluate these coefficients gamma L. Matthew, does that answer your question? Okay. Right. Okay. But yeah, or are there more questions? Okay. All clear? Then let's continue. Yeah, so the new statement of the theorem is just that there's a polynomial-time algorithm now to also sample metric graphs from this measure mu trop. And this polynomial-time algorithm, it works also recursively by following these kind of nonlinear recursion equations and lifting them to recursion equations on this modular space and on these metric graphs themselves. So I just took some pictures to illustrate here how this graph works. So it works recursively by sampling like a graph of lower loop order and then adding an edge, so closing external legs to form a new edge. And then we have to assign a specific length to this new pink edge via a specific probability distribution to get a graph with one loop order more, but two legs less. And so there's one algorithm that does that. And then there's another algorithm that just concatenates two random metric graphs by adding like a new edge between, by stringing them up, by putting them like up on a string. And there are specific weights we need to assign to these new edges that are being formed each time. So this algorithm recursively produces metric graphs with the correct probability distribution. And yeah, so the details are a bit technical, but this is how it works. So it recursively works and builds up these metric graphs. Yeah, any more question?
Yeah,
Yes?
the mu track, the mu TR, did it also depend on D or not?
Sorry, say again.
Your measure mu TR, it seemed like your previous equations for your tropical theory still had a D in them. So does
Yes,
so
it depends on D, right? Yes.
D, okay.
So in particular, it has to be finite. So the tropical, so we can only sample the graphs if we somehow restrict to a finite subsector of the original quantum field theory. So far, I mean, this is something that
the physical D or the same D as the real theory, or do you still have the nice properties with other D?
Yeah, so I mean, there are interesting things to ask about quantum field theories in lower dimensions, beyond the critical dimensions. So, for instance, in phi to the
Yeah, there are all these calculations. I was just asking as a, from the point of view of your arguments, you want your ratio to stay bounded and your variance to stay bounded. And is that true? If the D of the actual integrand and the D of this tropical thing, do they have to be equal?
Yeah, they have to be equal, yes.
Okay.
But I mean, this is, you just sort of solve the tropical theory in the dimension you're interested in,
Okay.
and then you can do that. Yeah. Okay, more questions?
Yeah, so I have a couple of questions. First of all, if I understand correctly, are you saying that you don't have to actually look at all the Feynman diagrams themselves, since they have L factorial number, but you only need to look at the ones that are actually important?
Yes, so this is exactly the trick. So this is completely in polynomial time.
Okay,
And these graphs, they are sampled.
We'll continue, but I'm going to ask after you explain if you have an estimate
Okay.
for the total variance.
Yeah, so these graphs are constructed recursively on the fly. So these are metric graphs with specific edge lengths. Yeah, you don't need to enumerate them all. And that's also what kill the polynomial time runtime immediately if you would need to enumerate them. Because yeah, so that would take factorial time to just write these graphs all down. So no, yeah, but yeah, so
Okay. But I have another question related to this ratio of the P, this denominator, and the tropicalized version. So you said that that ratio was bounded from above. So, but is there still a possibility that this is zero, like let's say very small, almost everywhere except from peak, like somewhere that you're not sampling? I mean,
yes, so this just guarantees that it works in principle, this Monte Carlo. So it's convergent, but it does not tell us so much yet about the actual variance, the value of the variance. So yeah, so this very much depends on how in which kind of band this factor here fluctuates. And I can show you like the actual empirical results about that later on.
Thank you.
Yeah, let's shift over to some empirical results, and we can go over, but we should stop after like 10 more minutes.
Okay, yeah, so I'm almost finished. Yeah, so here are some empirical results, and these are pretty basic still. So this is an example application for phi to the 3 theory in 3 dimensions. And previously, this has been known like by Feynman integral computations up to 7 loops by these people. It's the most recent result. And here I just computed a specific perturbative expansion coefficient at different loop orders. And I always took the same number of samples. So this is 10 to the 11 many samples. And here's the runtime. So this is 2 hours, 3 hours, 3 hours, 4 hours, 6 hours, and so on and so forth. So I computed this up to 20 loops. So this is a 20th coefficient of the 3-point function in massive phi to the 3 theory in 3 dimensions. So this is a model that is, for instance, interesting to study percolation theory in 3 dimensions. And yeah, you can compute these numbers pretty effectively. But as you mentioned, as one of the questions just mentioned, that the actual no, so yeah, so with this you can already get far further than like anything that is previously known. So this is like here up to 20 loops. However, and it's also not, it's a decent amount of time. So this took 24 hours on a on a, like, I mean, it's not a private computer, but it's also not a very big commercial computer. This is like a fast computer that we have here in the institute. And yeah, so this works quite well.
So
A
these errors
problem,
are the Monte Carlo estimated the variance?
yes, so here's the Monte Carlo estimated variance.
Right.
And this is the variance itself, it's bounded,
Yeah.
but that doesn't say so much about the relative error of the variance, because it's not only that the variance is bounded, it's also that the ratio of the square root of the variance and the actual value also has to be bounded. And what can happen in essence is that even though the whole thing is bounded, it can concentrate in a very small region of the phase space. And even though it's bounded from above, so it can become smaller and smaller and smaller, it can also become more and more concentrated in a specific little subset of the integration space. And this is also what is observed then here at these larger loop orders. So the error increases actually pretty rapidly. And I have theoretical bounds on the error here. And yeah, these bounds actually also grow pretty substantially. It's better. So this growth rate of this error, it's to a large extent actually due to the fact that we are thinking about a super renormalizable quantum field theory. So paradoxically, the numerics gets worse because we are in this finite situation. So that's why I also are actually focused on the so-called primitive beta function in phi to the 4 theory, which is another quantum field theory that is very interesting in 4-dimensional spacetime. So this has been known exactly up to 7 loops before, and using this tropical algorithm, there was a very nice large scale computation by Baldorf, who investigated these integrals up to loop order 18, which is about where this tropical sampling approach dies because of this exponential growth rate. So I computed this up to 50 loops, this primitive beta function contribution. So this is a specific sector of phi to the 4 theory that is still finite. So I don't need renormalization of this quantum field theory to make this work. This was something that I just didn't tackle in this work. So there's no renormalization. It's only about bare quantities that are not renormalized. So there's all the infinity still in there, and this is primitive beta function, is a specific finite contribution. Here, unfortunately, the times are not very representative because I changed the number of samples for specific loop orders because I wanted to get more digits in these specific loop orders. So for instance, at 15 loops, I wanted to get 5 digits, and also at 30 loops, I wanted to get also here a bit more than 4 digits. So I spent a lot of time evaluating these specific contributions just to get some idea on the asymptotics of these values of these beta functions, because they're interesting conjectures asking about the asymptotic behavior of these perturbative coefficients in this phi to the 4 theory that have very interesting relations to non-perturbative physics. So I wanted to investigate these kind of questions there, and this is now possible thanks to this global tropical sampling method. And yeah, here you can see that this growth rate of this error, it's actually much less pronounced. So it's still growing probably exponentially, and I have like a bound, radical bound that is exponential. And empirically, I find that this bound is, of course, very pessimistic. And yeah, so the growth rate of this relative error is still exponential, but it's at least not factorial anymore. So this improves a lot on this previous known bound, at least in this 4-dimensional, which is the critical dimension of phi to the 4 theory. All right, so some conclusions. So this gives a nice new approach to these QFT predictions or computations. It's driven by this tropicalized quantum field theory, and it resolves this deficiency of making that the predictions actually become harder than the measurement, at least in principle. There's many possibilities for extensions, and this is just sort of the tip of the iceberg. So far, I only did this for scalar QFTs, and also only super renormalizable quantum field theories where I applied this numerical algorithms, but I think this can go much further in different directions. So there's numerical problems that demand for improvements. These are precisely these issues that the mass, this probability mass, is very concentrated in this modular space. So even though the sampling works in polynomial time, the perturbative coefficients can take exponential time in the relative target accuracy. So if we want to fix a specific relative target accuracy, because the variance is growing so large, we might need to actually exponential time still, unfortunately. And I'm hoping that one can use like saddle point methods, for instance, to further refine this, and to also be able to focus like on these small regions of the integration space to improve this convergence. And then, of course, the last question is like, what's very interesting to me is what is the non-perturbative nature of tropicalized quantum field theory? Because all these proofs that I mentioned before, they only work perturbatively. But this PDE, this partial differential equation that I wrote down, it works also non-perturbatively. So we can also solve this tropicalized quantum field theory in this non-perturbatively. So there's a non-perturbative definition, but it's an open question. What does it tell us about the original quantum field theory before the deformation? And I think this is also very interesting. All right, that's it. I hope I didn't, yeah, sorry about taking longer.
Well, thank you. That was very nice. Thank you, Michael. Questions? Questions out there? I'll just comment that you may know there's a variety of ways of constructing non-perturbative field theory that the mathematicians do, and it's very frequent that they continue to non-integer dimension and non-integer weight, fraction, exponent on the kinetic term and so forth. So there might be relevant results for you there.
Yeah. So I'm in contact also with some people who think about functional randomization group in this direction. So yeah, so this might also
help. I was thinking of like there's a stochastic, rigorous stochastic quantization literature, but many approaches. Yeah.
I have a question, but I couldn't figure out how to raise my hand electrically. With high order, with the successful high order table that you showed, do you have enough precision to do a Pade approximation of the power series and maybe get some idea of where the poles are?
Yes, so this is exactly where these conjectures, why I investigated this. Let me just sort of, So this large order behavior here, there's conjectures so equivalently, so there's different formulations. So there's conjectures on the large L behavior of these coefficients here, for instance. Actually, there's a combination of conjectures because this is a specific contribution to this phi to the 4 beta function. And it's actually a conjecture, first of all, that this specific contribution dominates the beta function in a specific randomization scheme. And that's the minimal subtraction scheme. And in this minimal subtraction scheme, there's then again a computation using instanton methods that predicts the large order behavior of these coefficients. And therefore also the location of poles in the Borel plane if you want to resum these coefficients. What I can say about this so far is that the location turns out right. So, so the exponential growth rate agrees with the prediction, and perfectly so. But then there's like constant terms and also power law terms even sometimes that are not so clear on how to interpret them and relate them to these conjectures. The problem is that there's a chain of 2 conjectures. So I can say with confidence that both these conjectures cannot be true. So it does not match the expected behavior, but it's unclear where it fails. So it either could mean that this primitive contribution does not equal this minimal subtraction beta function in the large loop order limit, or that also these instanton computations are instanton predictions are false. But yeah, so it's a different question what of these 2 things are false. Yeah, and then also I didn't mention this, but to go forward here, the obvious thing is of course also to just do the randomization and renormalize these computations also numerically and perform like a computation in a specific randomization scheme and compute like the beta function in some scheme and then ask about the asymptotic behavior. But yeah, this is future work. So the next step would be to really try to include randomization.
Right. Okay, well, thanks. Let's thank Michael again for a very interesting talk. And next week we'll have Alex Damian of our own Harvard Applied Math, and he'll speak about understanding optimization in deep learning with central flows. So I hope to see you all there. Thanks again.
Thanks for having me.
Thank you, Michael.